Hi, in this lesson we're going to discuss the first subunit of the topic 4, oscillations. Firstly, what are oscillations? Oscillations are periodic motions which center around an equilibrium position. For instance, a simple pendulum and simple harmonic motion are depicted in this diagram. These are the most well-known examples of oscillations. One oscillation is made, for example, in a simple pendulum when the bulb makes one full circle. In this unit, we will use 4 different terms. Period is the time to complete one full oscillation. It's measured in seconds. Frequency is the number of oscillations per unit time, measured in hertz or seconds in the power of -1. Displacement is the distance from the equilibrium position, and the amplitude of the oscillation is the maximum displacement from the equilibrium position. Displacement and amplitude are measured in meters. As depicted in the diagram below, the amplitude or the maximum displacement of this simple harmonic motion is here. Period is calculated using the formula 1 divided by frequency. Here is a question from a past paper. A girl in a stationary boat observes that 10 wave crests pass the boat every minute. What is the period of the water waves? Frequency is 10 waves per minute. We use the formula T equals 1 divided by frequency. Therefore, the period is 1 divided by 10 minutes. Now let's move on to the force and acceleration in simple harmonic motion. A restoring force is required for a system to oscillate. In other words, restoring force brings the system back towards its equilibrium position when the system is displaced away from equilibrium. When the system undergoes periodic oscillations, the direction of the restoring force and the direction of the acceleration are always towards equilibrium position, as shown in this diagram. For this unit, the definition of simple harmonic motion is acceleration is directly proportional to displacement but in the opposite direction. When the displacement is 0, acceleration is also 0, but velocity is maximum. When the displacement is maximum, acceleration is also maximum, but the velocity is 0. There are 2 questions from past papers. First one is, the graph shows the variation with position s of the displacement x of a wave undergoing simple harmonic motion. What is the magnitude of the velocity at the displacements x, y, and z? At x, the displacement is maximum, therefore velocity is 0. At y, displacement is 0, therefore velocity is maximum. At z, displacement is 0, therefore velocity is maximum. Hence, the answer will be B. The next question says, what is true about the acceleration of a particle that's oscillating with simple harmonic motion? A. It's in the opposite direction to its velocity. B. It's decreasing when the potential energy is increasing. C. It's proportional to the frequency of the oscillation. D. It's at a minimum when the velocity is at a maximum. The correct answer is D, because as we said earlier, when acceleration is 0, velocity is maximum. Graphs describing simple harmonic motion are an important part of this unit. So the first graph that we'll discuss is an acceleration displacement graph. Main feature of this graph is that there is a straight line with a negative gradient that passes through the origin. Gradient is negative because in simple harmonic motion, acceleration is directly proportional to displacement, but in the opposite direction. Next graph is the displacement time graph. In the diagram, a displacement time graph related to displacement of the object is presented. Let's recall the gradient and the area of different graphs. Gradient of the displacement time graph gives velocity, gradient of the velocity time graph gives acceleration, and then area of this graph gives displacement. Area of the acceleration time graph gives a change in velocity. There you can see examples of velocity time and acceleration time graphs. Here is the question from past papers. A particle undergoes simple harmonic motion. The graph shows the variation of velocity v of the particle with time t. What is the variation with time of the acceleration of the particle? In this question, the velocity is maximum at time 0. Therefore, acceleration should be 0 at time 0. That's because when the velocity is maximum, acceleration is 0. The correct answer will be A, because when the velocity is maximum, acceleration is 0. When velocity is 0, acceleration is maximum. When the velocity is maximum, acceleration is again 0. Now let's talk about the phase difference. Phase is stated as an angle. We usually measure it in radians. The two curves on the graph take the shape of a sine curve but start at different points. There is a phase difference between both curves. That is, the graphs are pi divided by 2 radians out of phase with each other. There can also be a case when there's a zero phase difference. In such situations, graphs are in phase. The question says a sound wave has a wavelength of 0.20 meters. What is the phase difference between 2 points along the wave which are 0.85 meters apart? Here is the diagram for this question. The wavelength is a distance between two crests, so it's the distance here. So let's take this point at the beginning of our graph. And the point lying at 0.85 meters is located here. As the phase difference is constant in this graph, for our convenience, we can choose any point that's parallel to this point. Let's choose the point right next to our first point. One full oscillation ends here at 360 degrees. Half oscillation ends at 180 degrees. And the half of the half oscillation ends at 90 degrees. Therefore, these 2 points are 90 degrees out of phase. The phase difference between displacement and velocity is pi divided by 2 radians, and the phase difference between displacement and acceleration is pi radians. The last topic of our lesson is energy transformations in simple harmonic motion. In simple harmonic motion, kinetic energy converts into elastic potential energy and vice versa, and the total energy remains constant. In this diagram, one cycle of an oscillation is depicted. The question from past paper is a particle is displaced from rest and released at time t0. It performs simple harmonic motion. Which graph shows the variation with time of the kinetic energy of the particle? We can eliminate answers A and B because energy can never be negative in simple harmonic motion. C is not correct because the particle is displaced from rest and released at time t0, which means that kinetic energy should be 0 at time 0. Therefore, the correct answer is D. So this is all for today's lesson. I hope you enjoyed it and found it interesting and helpful. See you next time.